after all the discovery of primordial of black holes with gravitational waves and stuff. I found this very interesting to have primordial black holes as particle sources in the early universe. So just if someone is interested, I just gave like a couple of recent reviews on primordial black holes, like primordial black holes as dark matter or primordial black holes in the early universe as particle sources. So maybe I can start saying that we know that in order to have very light black holes in today's universe, we would require a specific, it's basically sort of impossible as far as we know, because in order to have black holes form from a stellar collapse, we know that there is a limit for the mass that these black holes would have. So if we want to think if we can have black holes that have, I don't know, are very light, we would require higher densities or a different process to produce this. And you can find this type of, let's say, environment in the early universe. So basically, if we want to have black holes in the early universe, the thing is that we know that the early universe was very dense. But this is not like this is a necessary but not sufficient condition to form black holes in the early universe. So in principle, you also need to have some sort of homogeneity that will somehow collapse and form a black hole. So in general, you can parameterize what is the mass of a black hole that can be formed at a given time in the evolution of the universe. Just because if you know that the maximum amount of mass that a black hole can have is like related to the particle, to the Hubble horizon mass. You know, this is the largest mass that it can have. So the mass is related. Let's say I'm going to call initial mass. It's proportional to the horizon mass, which basically is proportional to Hubble as function of time inverse. Or when if we assume an initially radiation-dominated universe, what we have is like the initial mass is basically related to time like this. Or if you put some numbers, like if you can have a black hole formed with this mass of 10 to the 15 grams at about a time of 10 to the minus 33 seconds. So I will apologize. I apologize for the handwriting. It's not the best one, but I will try my best. So okay. So in principle, this is like a general idea of what is the mass of a black hole that can be formed at a given time. And this is a relation that tells you, well, if you want to have lighter black holes, you need to go to earlier times. So there are many mechanisms that people have proposed to form black holes in the early universe. Let's say,
if you want to have lighter black holes, you
yes.
have to go to earlier times? But
yes.
Why can't you have, that's the maximum mass it could have.
Yeah, but yeah.
So why couldn't it have lower than that mass at later times?
Well, it depends on the formation mechanism, right? Yeah,
okay.
Yeah. It depends on how you're going to form its black hole. But this is more or less the idea. Like, the simplest scenario is related to this mass, right? But in principle, the thing is that if you want to form a lighter black holes, you need to surpass pressure and stuff like that, right? So this is it's a way to tell what is the mass that you can form at some given point.
Okay.
How heavy is the sun?
Let me just write here, 10 to 33. I don't remember. There is a number. It's very light. And this number will come back because of reasons I will talk later. I don't have the number, but yeah, I'm not sure. I don't remember. No, I don't remember. I thought I had read one. Yeah, I think it's, well, I don't remember. I don't know that for solar masses, if you want to have a formation of black hole of a solar mass, you can go to the time when you have QCD, the QCD transition. This is the time, so it's earlier than this. Okay, so there are many different mechanisms that people have proposed to form black holes in the early universe. The most known, or what people have worked most, is considering the collapse of gravitational perturbations after inflation. So you have inflation. Inflation basically, you start with quantum perturbations. Inflation makes them macroscopic. And if they are above some threshold, because you need to go above some a specific, this have a lot of pressure. So above a given threshold, if these perturbations are bigger than this threshold, they will collapse and form a black hole. So in principle, so what you need is that, let's say this is like, the contrast density should be larger than some threshold. Oh, it's not rho, it's delta, some threshold. And the threshold is related to the conditions of the universe. For instance, if you have some pressure, you have radiation, this will depend on the pressure, because this is something that, if you want to form a black hole, you need to go against the pressure of the radiation, right? So you need to go smaller than the Jeans length for a given time. Okay. So in principle, what you can imagine is that the spectrum of inhomogeneities is like, this is the wave number. So maybe we have that this spectrum had some peak at some given value. And when this perturbation re-enters the horizon, it basically will collapse, forming a black hole. In this case, what we find is that, what people have found is like the initial mass will be proportional to some gravitational collapse factor, because it depends on the conditions of the universe, times that horizon mass. Okay, but this is one case, right? And people have shown if you want to have larger amounts of black holes, these perturbations are a bit, let's say, very different from what we expect from CMB. So there is a bit of a tension in the simplest cases that you analyze from inflation. So there is a bit of a tension because minimal models struggle to deal with this. But again, yes. Well, I don't know if, we don't know because this can happen before BBN, right? So we don't know the specific conditions of the universe. But in principle, that's the struggle because we know that the CMB is very low, but we don't know, we don't have any access of what happened at high redshift, right? Yeah, you can compute. But yeah, the thing that you find is that if you want this, I don't know, at CMB, and then form very heavy black holes like this, the scalar potential of your inflaton has to have some specific features. So it becomes very model dependent because it depends on how you write the potential. If the potential is low, if the field is rolling down, yeah, or stops or something, yeah.
So what type of features do you expect?
So in general, I think the potential. So you have the rolling down, but then if there is a period in which basically it's not rolling down, but it's like sort of ultra slow rolling down. This is when they expect that you can have larger perturbations. And then, but still you need to, again, go to see what you know about CMB.
Is there any inflation model that gives you this?
Yes, there are, but they're a bit contrived. Because in principle, people either because you need to fine-tune the shape of the potential. Or you can have multi-scalar inflation. And then people have started working on this. But okay, this is not the only way, right? Because in principle, you can imagine that if you had some phase transition in the early universe, people have shown that depending on the conditions of your model, if these bubbles collide and if you have, I don't know, matter between the bubbles will basically squish matter, and then you can form a black hole. But again, this is model dependent because it depends if the particles outside the bubbles, if how they wouldn't enter the bubble. For instance, if you have that inside the bubble, a particle gets a mass, but outside is massless. So for energy conservation, you know that this particle needs to have a larger energy. If it doesn't have a larger energy, it cannot enter the bubble. So it basically gets squished, and then you form a black hole. But again, this is like model dependent. Other things that other people have proposed is like, you can imagine that after inflation, you had some particles, new fermions, that interact via some specific Yukawa force, and the Yukawa force is more efficient in forming black holes than gravity. This is another possibility that people have considered in general, like to form black holes.
Long range?
Yeah, long range, yeah, Yukawa-like.
So what's the mediator?
Yeah, it's, they assume a scalar mediator, so basically you have, I don't know, After inflation, you create these fermions, and these fermions start to interact. We have this long-range interaction, which is stronger than gravity. They clump, and they start to form black holes.
But those are very constrained.
Well, I think
Fifth force kind of.
well, but it's fifth force, but the mediator can be it's basically tuned such a way that is for the early universe can be considered massless, right? So it's well not exactly massless, but the Yukawa mass is very smaller with the respect to the temperature.
Sorry, the fermions, we don't know what they are, so who cares
Yeah.
what the mediator is,
Yeah,
right?
yeah.
What do you mean constraint? There's no constraints on it at all because we don't have any of the particles today. Oh no, if
Yeah.
But we never mentioned standard model.
Yeah.
No, but we never mentioned that.
Yeah, it's they assume another sector. But okay, so what I want to talk from now is like I will assume that somehow, since there are like several ways you can form black holes, I will assume that there was the initial population of black holes. So this is an assumption that we are considering. So I will be sort of agnostic of what is the formation mechanism that they produce these black holes. Let me just erase this. So basically, these black holes will be parameterized by some initial mass and by beta, which beta is basically what's the amount of primordial black holes that form at the initial time. So the energy density that went into black holes with respect to the total energy density. So this is like the two basically parameters that I'm going to assume that are fixed because some specific model. So this basically tells you what is the initial mass and what is the initial abundance of black holes that you have in the universe. So if we assume that these black holes formed, at some point, since basically it depends on the initial properties, if we consider that Hawking radiation works as we expect it to work, basically these black holes start to emit particles, and at some point, depending on their initial masses, they can basically evaporate, right? So when does this become important? So basically, quantum effects are important depending on the Schwarzschild radius. I will first assume Schwarzschild black holes, so they are only characterized by their mass, nothing else. So when the Schwarzschild radius, given by this is like the instantaneous mass, so black hole, is of the order of a Compton wavelength of some particle. So when these conditions are met, the black holes, quantum effects become important, and then black holes start to emit particles from the horizon, or close to the horizon. We don't know yet exactly where from, but yeah, they start to emit particles and reach infinity. So maybe I can do a quick detour on the derivation of Hawking radiation, just to put everything, all we agree. So let's just. Yes.
People will know, I think.
Yeah, well, I don't know if yeah, no, I won't go into details because I don't have time. But of course, I just want to give like the general idea of how Hawking radiation is. So I'm going to start with the Penrose diagram. I hope people don't mind with this. So the idea of a Penrose diagram is just you're going to show the whole space-time in just one figure. In, let's say, in a very short way. So basically, if you have the formation of a black hole from gravitational collapse, this is sort of the Penrose diagram. So this is basically where the singularity is. This like, no, sorry, let me do this. Going back to what is everything. So this is the past time-like. This is the future time-like. So oh, sorry, this is the future. This is the past. this is spatial infinity. This is the past null infinity, and this is the future future null infinity. So basically, this is like the description of how a black hole, basically you have an initial star that collapses, and at some point it crosses the horizon here. It's not very nice. Oh yeah, that's better. It's a horizon. So sorry, I won't give the details how this comes from. Just saying that light propagates in 45 degrees. So it's basically massless particles propagating 45 degrees. So the idea is that let's assume that there is the existence of a scalar field that lives in this space-time. So this scalar field, for instance, will obey some sort of wave equation, where this basically the D'Alembertian is related to the space-time that I'm going to assume to be Schwarzschild. And basically, if you want to solve this equation, I'm not going to the details, but you can do some. You separate variables. And then you obtain some, let me just write what is phi. Some. Right? And then you basically obtain an equation for this function that only has the dependence on the distance, on the distance r. These are basically some sort of the eigenvalues, right, for the angular part, as we know. So this gives me an equation. Okay, so basically this, what I'm calling a potential, is basically a result of doing this separation of variables. And this is sort of a potential that comes from the fact that the space-time is curved. You can see it as a potential, and it will act for what will appear later as a potential. So if you can imagine, this is normal wave equation when you are including some specific potential. And the shape of this potential will depend on the space-time. So what am I doing this, right? So the idea is that we want to assume that in the past, before the black hole was formed, there were no particles. So here in the past null infinity, where is the other color? So if you have, like in the past, there were no particles, and basically space-time was flat, you can basically try to solve this equation for a flat space-time, and then assign some sets of, because of this solution, basically will form a set of functions in which you can expand anything, right? So before the collapse here, I'm going to define a complete set F. And after the collapse, basically these are solutions of this equation of motion for this equation of motion in the past. But after the collapse, then you can have different coordinate system, right? And then you can assign a different complete set that will live basically in this boundary, in the future null infinity, and also in the horizon. You need both, right? So basically, you have like here you will have J, a different set. Okay. So the idea is that still I'm working in the classical level, and then I'm just going to try to quantize this field. Again, I'm basically going over many steps I'm just going to give you results. So the idea is that I can basically expand my field after quantization. I can expand my field in the in basis. This is what I'm going to call the in basis. And you will have some, let's just consider one dimension. And then you can expand in sort of a basis. Okay. But also, after the collapse, or basically you can expand your fields in the other basis that I'm going to call the out basis. Okay, so in principle, I haven't done like anything specific. So what I'm gonna assume now is like, oh, okay, let's assume that before there were no particles. So this means that I'm gonna assume that the initial state is a state in the in basis, which is vacuum, right? So there are no particles related to this in field in the initial basis. And then I want to see what is the number operator. So basically this means that if k applied into this vacuum is 0, right? So the question is what happens if we compute for instance, the vacuum expectation value of this state in the other expansion of the field. So basically you have, let me just call this okay. So in order to compute this, we need to relate to the two bases, right? And to do so, we basically employ the so-called Bogoliubov transformation, right? Because it's basically a way to relate these two bases. And it comes from the fact that you can relate these two bases via some specific transformation. Again, I'm sorry, I'm skipping many details, but the important thing is that I can write my basis, my operators in the basis out as some functions here. It's minus here. Dagger. So when you basically employ this and compute this expectation value, you find that this is basically, let me just be careful with the indexes. So this will be non-zero. This means that basically you will have that if you look at the vacuum, the initial state, if you had an initial state here, in the future, you will see that this vacuum is full of particles, right? So now the question is how to compute this. And sorry, then I will skip everything, the full derivation, because it would take more than an hour for sure. So when you compute this, and this is basically the idea of the paper of Hawking, is basically how do you compute these coefficients using the shape of your spacetime, using this Penrose diagram. Being smart of how you basically compute the different, like what is the last line, what would be the last ray that reaches the future null infinity. But again, I'm going to skip. This gives where the Hawking temperature basically is basically the temperature related to the mass of a black hole, the instantaneous mass, and this is about 1 GeV for a black hole which has a mass of 10 to the 13 grams. Okay, but there are still these quantities here that basically are telling us that even though, of course, I am assuming a scalar field, right? But there are these quantities that are telling us that you are deviating for a full body, black body spectrum. And the reason is that, as I was mentioning before, the space-time is acting like a potential, right? So in principle, you can have a reabsorption from the black hole because you can have basically some part of the waves are reflected and others are transmitted. So in principle, this becomes sort of a problem of close to quantum mechanics too, and is basically computing transmission coefficients for, if you forget about the origin of the equation, it's just take what is this equation and take this as a potential, and you compute these transmission and reflection coefficients. So what I'm going to do is like, there's no derivation, it's usually done numerically, but the important thing is that this will be a crucial quantity for what I'm going to talk later. So basically, instead of considering this absorption probability, people usually talk about some sort of absorption cross-section. And of course, since we are in 3 dimensions, it will depend on the partial waves of each, I don't know, it depends on the quantum numbers here, L and M. Okay, but maybe it's more interesting to show a plot. So here is like sigma. This is basically the energy or the temperature. Okay, so when you compute for this, each specific type of particle, instead of having only scalars, but also having fermions, vectors, and spin-2 particles, you find that they have like, they tend to this classical limit, which is this 27 pi G square and M square, which is basically if you had a classical wave impacting of a black hole, you can compute that this is the cross-section. This is like the classical value. And if you have, but of course, when you have an scalar other particles, this will happen when this energy goes to a large value. But for lower values, what happens is that these have some specific shape. Let me try to do. So this is for scalar. Let's put here. For a fermion, that's from a value non-zero. For a vector, like and for a spin-2, I won't draw just because of the colors. Bye. Sorry?
These are all massless? These are all massless particles?
Yeah, everything is done massless so far.
And why are there differences between, can you say?
Yeah, so the thing is that, let me just explain before. Each oscillation is related to the different partial wave, right? So because you have different partial wave. So the difference comes from the fact that the specific potential will depend on the spin of the particle, because it comes from the equation of motion of the particle. Okay. So they have a different shape. So at the end, this is why you have like different forms for this.
Yes, but this is nothing to do with Hawking radiation, no? It's just the scattering of...
Yes, yes, yeah.
Okay.
Yeah, but this quantity is the one that will basically modify the Hawking spectrum. And given a bit of a spoiler, it will tell you that the emission for the Schwarzschild black holes of higher spin particles is a bit reduced. Because you can imagine that these functions are multiplied by the bosines, right? So in principle, if you look here, I'm like around 5. So it means that, so I was going to put this actually, sorry. This black, white is 1, and the green is 1/2. So the one that will dominate the Hawking evaporation will be this yellow, which is basically scalars, then fermions, then vectors. And if you have a spin to particle, it's even worse. It's like, yeah. Yeah. So it really is the emission of gravitons. So the idea here is that the emission of gravitons or higher spin particles is very suppressed because of these quantities.
Yeah, I mean, it's analytic, no? For omega going to 0 is 2L plus, 2L plus S.
Yes, yeah, there is a, yes. But okay, so this was basically the detour from Hawking radiation that I wanted to say. If there is any question, please just let me know. I know that I skipped many details, so I apologize for this. But okay, the idea is that, well, since black holes are emitting these particles, they will have a finite life, right? And how can we estimate what is the lifetime of a black hole? Basically, what we can do is...
Sorry, you want to use Hawking radiation when the black hole is very small also? You want the black hole to evaporate completely?
Yes.
I think we don't even understand that process.
Yeah. I'm not going to assume what happens at the final stages. So we don't know what...
But that may change everything.
Well, the thing is that the semi-classical approximation that Hawking used breaks down when the curvature gets close to the Planck scale, right?
Yeah. It's a macroscopic mass evaporating. So if it leaves a Planck remnant, it doesn't change the phenomenology.
Yeah.
Okay.
I mean,
I'll take your
of course,
word for it.
this is still higher, much higher. This is, can be semi-classical. Even if I go, I don't know, to a 1 gram black hole.
I'm just saying you're ignoring all quantum effects. You're just using semi-classical
Yes.
effects to describe a very quantum process.
Yeah, well, yes, this I think.
This is semi-classical. It's quantum only when the remnant is close to the Planck mass.
Yeah, but he's concluding that. Anyways, keep going.
Yeah.
No,
I mean,
I'm more worried about X-ray emission that we don't see. I mean, if this object is evaporating, we would see plenty of X-ray emission that we don't.
Well, yeah, I will come back to the constraints later because I'm just being a bit general here. But yeah, I will come back to what are the constraints on this and how these black holes are constrained. Yeah. Okay, so when the black holes start to emit particles because of this particle emission, of course, you can estimate what is the mass loss rate just by energy conservation. I am writing very badly.
I cannot resist to make this comment every time people talk about Hawking radiation, but this is for NATO more than for you. This process is not really quantum. It's quantum only once you introduce the temperature. To introduce the notion of temperature, you need H.
Okay.
Because you see H omega divided by temperature, H and H simplifies.
Okay, so basically, where is that? Basically, in order to compute what is the lifetime of a black hole, basically we can estimate by computing the energy of a given particle which is emitted times the probability rate or this rate that depends on the energy and time, the Hawking rate, integrating over the energy. So this Hawking rate, of course, it will be... When you go back and look at what this means, this actually means that this is a rate of emission of particles, because if you integrate this, it will give infinity, but you need to be careful when you compute, again, everything. So what you find is this is a Hawking, an emission rate of particles that depends on the instantaneous mass of the black hole. So this. depends on the degrees of freedom of particles, and now I'll write in terms of this cross-section. Or energy, sorry, changing here. Okay, so it basically will tell you, it will depend on the degrees of freedom, they will depend on this quantity here, and it will depend on the spin of the particle, just writing in general Bose-Einstein and the Fermi Dirac here. So you can basically use this form for the Hawking emission rate and rewrite this mass loss rate as follows. Will depend on what is called evaporation function, Planck scale over m squared. For me, Planck scale will be 1 over g.
So just to understand, I think I talked with you about this before, but so you assume that the black holes were formed, everything is in the black holes, and then they evaporate. Is that the idea?
Well, the thing is that you don't require a larger amount of black holes to be formed. You can have a specific amount that will depend on this parameter.
You don't have any particles outside the black holes.
Well, yeah. So far, I'm not considering any black holes in a bath, not yet.
So you just have everything falls in black holes, and then suddenly all the black holes decide to evaporate.
No. Again, in the universe, so I haven't got to the specific case of the universe. So this, sorry, maybe I wasn't clear.
Okay.
So this is, I'm going to assume first a population of black holes. Yeah. So this is like the Hawking evaporation for one black hole in vacuum. Okay. But in principle, you will have a population of black holes that they start to evaporate, right? But it's not that like all the radiation you had became black holes. Okay. It will parameterize by this. So even the interesting thing is that even if you have a tiny amount of black holes, they could lead to a domination of the energy budget of the universe. So yeah, sorry, maybe I'm skipping some details, but yeah. So what you find is that the emission rate of, that the mass loss rate of a black hole, it's inversely proportional to m squared. So this means that at the beginning it is sort of slow, but when the mass starts to shrink, it accelerates, and at some point it becomes so fast that it's sort of an explosion. What happens when the mass of the black hole reaches the Planck scale? This is the thing we don't know, right? Because in principle, at that point, the semi-classical approximation that we're using here breaks down, because it depends. It was computed only when the curvature is bigger than the Planck scale, so that will break down. But the interesting thing for us is that this evaporation function here. Basically, sorry, I forgot to mention here that my sum is for all degrees of freedom. So all existing degrees of freedom in nature. Not only including degrees of freedom of the standard model, but also degrees of freedom that are in models that they, for instance, don't talk with the standard model.
Temperature is high enough to accelerate.
Yes, exactly, yeah. But in principle, you can have some light physics that is produced, but they don't talk with the standard model, right? Yeah, but for me, the interesting thing is that this will create all particles independently if they interact with the standard model order. And then you can start to look what would be the consequences of having this in the early universe. So this evaporation function will contain the information. It will contain, basically, we will tell you what about these degrees of freedom. Yeah, we'll skip this figure, that's because of time. But okay, yeah, so this is basically the general idea of how Hawking evaporation works and how would the mass of these black holes be evaporated. But yeah, let's go back to the case of black holes in the early universe. So the thing is that when you compute what is the lifetime of a black hole, you can estimate, well, what would be the lifetime of a black hole that would be evaporating to date? So this, I mean, what would be the mass of the black hole that has a lifetime equal to the age of the universe? When you do that, you find that it's actually this value is close to the 10 to the 15 grams. So this is what we were choosing, this value. Because if you have black holes that are heavier than this value of 10 to the 15 grams, they would be still around, and they could be part of the dark matter. This is assuming the standard model, sorry, I forgot to mention. So, of course, if there are more particles, they will evaporate faster. But if a black hole had a mass, an initial mass bigger than 10 to the 15 grams, it could be still around. So it could be part of the dark matter. If it was lighter than this, it would have evaporated in the early universe.
Ignoring quantum effect, right?
Yeah, yeah, yeah.
And you assume you can ignore. I just don't understand why you assume you can ignore.
Well, I don't know how could you incorporate these quantum effects? How do we know
From the
this
start.
effect?
That's why I think you're dead from the start. You're ignoring important effects. I agree. I don't know how to include them, but I don't think.
So I think I think we're just using the tools we have. That's what my assumption.
The curvature scale is way longer than the Planck length. So why are you so worried?
You can ignore them, but he hasn't said. He said it evaporates. You don't know when it evaporates if you don't know quantum effects, right? We don't even know if they evaporate completely or not, I guess.
But this is only will matter for a specific case by the end of the lifetime, right? When the approximation of Hawking breaks down.
Yeah. So if you can argue that when it breaks down, it's irrelevant for your computation, I'm happy.
Yeah,
but
It's basically, Well, it will depend for some limits, some constraints that people have thought.
Okay.
It will depend on that.
Okay.
I mean, from that mass to the Planck mass, you still have 20 order of magnitude. So
Yeah, the Planck mass is 10 to the minus 5 gram. Okay. Okay, so let me just, as I was saying, so depending when the black holes evaporate, if the time when they evaporate, they change any cosmological observables, the constraints will be very strong. For instance, if the mass of initial of the black hole I don't know, it's about 10 to the 10 gram, they will evaporate during BBN. So we know very well the predictions of BBN, and then the constraints that you have in this case are very strong. So let me just do a plot about this. Let me just write here, these are my two parameters and my figure. So as I was saying, 10 to the 15 grams here. So the initial mass in grams. I go to about 1 gram. And this is beta. So this is about 10 to the minus 30. Sort of. Yeah. So as I was saying, there is here the boundary. It's not exactly this value. It's close to this value. So if you had, this could be part of the dark matter, and these black holes would have evaporated by now. So depending on when they evaporate, as I was saying, the constraints could be very strong. For instance, if you had 10 to the 9, this 10 to the minus 20. You have some constraints here. Oh, sorry. That coming from BBN. If they evaporate a bit later, so what they start to affect is the CMB. So constraints are very strong here. And then you start to constrain, here, you have extragalactic gamma rays that you don't see, so you also have very strong constraints here. Look at the values of this initial fraction. And if you go to this side, you have constraints from, sorry, maybe it's not exactly good, cosmic rays, because again, if these black holes are evaporating today, they would produce very energetic cosmic rays that we would see. And at some point, the constraint is that if you're above some line, let me see if I do it correctly. Yeah, they would overclose the universe. They would have a larger value of omega dark matter.
Also microlensing, no?
Yeah. So yeah, sorry, it's because it's a bit difficult to draw, but yeah, I think
It's for higher masses.
yeah, I think it's 10 to the 20 because there is a window still open, right? Which is I think between 10 to the 17 to the 20, and then you have this microlensing constraints. Yeah. But if you go to the early universe, so basically it's not that we have access to the physics before BBN, then you start to assume some things in order to put constraints. Some of the things that people do is like if you assume the minimal supersymmetric model and you assume that, for instance, one of the particles is the lightest, you have the production of black holes. They will not only produce standard model particles, but also supersymmetric partners. And if one is lightest, then you will have probably the production of dark matter from the LSP. But again, this is model dependent. So you can put some constraints here. Again, now if you assume this is 10 to minus 20. If black holes have a mass of smaller than about 0.1 gram, they would have been formed before inflation, so they will be diluted. So in principle, there is an inflation. And then there is another constraint here that it really depends on the assumptions of what happens at the end of the evaporation. Some people say, well, the evaporation stops and then it leaves a relic. And this relic could be basically produced by these black holes here. So in principle, if these relics do exist and if they have, I don't know, masses a few times the Planck scale, they say, oh, this could be, they will behave as dark matter. And then if you are above this line, they would have a larger value of omega dark matter. But again, this also depends on what it's assumed about the final stages of the evaporation of the black hole. Okay. So basically, the idea is that before BBN, we don't have, constraints are model dependent, are very model dependent. Okay, but in principle, if we assume that these constraints are weak and we think that they may be, if you don't have any supersymmetry or you don't have any other things, this basically tells you that this parameter space is basically open. So what would be the consequences, for instance, of this, of having black holes with even these small amounts in the evolution of the universe, right? So this is basically the question we want to ask now. So I will focus on the region that I was just mentioning, like 0.1 gram. Then to the 9 grams, which is basically this boundary. After that, constraints from BBN are very strong. So I will assume that black holes are relatively light, and then ask what happens if you had some particle process in the early universe happening at the same time with this black hole evaporation. So if we want to describe this more accurately, we need to solve these equations, the Friedmann-Boltzmann equations. Basically, let's change this one. So we will have a universe that contains radiation, and
Sorry, up to now, this is all revealed.
yes, I'm going now to what I have been working on. Yeah, so the idea is that you will have these Friedmann equations for the standard model radiation and for the black holes, right? So the standard model, oh, sorry. Row of black holes. So basically, you will have a source term of the black holes evaporating into the standard model, right? Depending on the amount of initial density that you have at a given time. Then you have the evolution for the black holes. So basically, this is telling you this is depleting the amount of black holes because of evaporation. So I'm putting a might be not clear sign here because it's minus, but just recall that the DMDT has a minus sign. So this tells you that this is actually a positive quantity, right? So it's increasing the amount of standard model radiation. And this one is basically telling you that this is depleting the amount of black holes you had in the early universe.
Are they really not relativistic?
Well, they are assumed to be like matter.
Yes, but I mean, compared to the temperature of the universe.
Oh, well, it depends on because at some point they can be relativistic, but at some point, the temperature of the black hole can be higher than the plasma.
No, but I think here you're assuming they behave like non-relativistic matter, right?
Yes.
So this is true only from some temperature of the universe on.
Yes.
No,
I'm not sure.
Yeah, probably it's a very good assumption. I was just wondering if anybody bothered to check it.
I don't think someone has checked that, actually.
Okay, it should be straightforward anyway to
Yeah,
convert the temperature into mass.
Yeah, you have to see. Yeah, you're right. But yeah, yeah.
Oh, but yeah, these are super Planck. I mean, so yeah, sure.
Yeah.
They are
That-
non-relativistic.
yeah. Okay, so the interesting thing is that since we are going to assume that the black holes behave as matter, even if you had a tiny amount of black holes, you can have a domination of these black holes and of the early universe, right? You can have a period of early matter domination that is basically there because of the black holes. In principle, this early matter domination will end when the black holes evaporate, and then you reheat the universe, but the reheating of the universe will come from the Hawking radiation that is basically populating the standard model here, right?
No, but wait, it depends on the beta if they can
Yeah,
dominate or not.
yeah. That's what I'm gonna write. Yeah. So yeah, exactly. So it depends on the initial amount of the black holes that you have. And the interesting thing, what I find is that you don't really require a large amount. So basically, in order to compute that, I will skip that, the derivation. But you just compare if they can dominate before they evaporate, right? Because it is the key for this. They can, if they don't dominate before evaporating, you don't have this early matter domination. This will happen for beta larger, approximately 10 to the minus 13, for a black hole of 10 to the 8 grams. So it's quite a small number. It's not, you don't need a large number of, a large abundance or initial abundance of black hole to have matter domination. And I think this is quite interesting because it's telling you that, I think it's, try to draw this. You are in this region here, you can have PBH domination. Yeah, maybe the line is not exactly in the point, but yeah, we just try to do it correctly. Yeah, it's actually a bit of a high. Yeah, sorry. Yeah, sorry, it's much higher. Yeah, I didn't draw it correctly. Yeah, sort of. 5. Yeah, so. Yeah, sort of. Yeah, sort of. So this means that you don't need a large amount of black holes that in order to have a domination of the universe. And I think this is interesting because you can start wondering what happens if you have any kind of particle process in the early universe that can be modified because of the presence of these black holes. So for instance, something that we have working on is like, what happens if you have, I don't know, freeze-in or freeze-out models in the presence of these black holes? Because as I'm saying, you can have a tiny amount that is produced from inflation or for something else, and then you can have this period of early matter domination. But it's not only a matter domination, right? Because at the end of the lifetime of the black hole, you will have a large entropy injection, because this rate really grows at the end of the lifetime. So basically, they will inject a lot of entropy by the end of their lifetimes. So this tells you that depending on when a particle process happened, you can have different predictions, and it will depend on the amount of black holes you had in the early universe. So for instance, let me just, I think, separate specifically what I mean by this. So let me just draw the evolution of the standard model radiation and the black hole energy densities by multiplying rho a to the cube. So radiation evolves here as 1. So, rho standard model evolves to the 10 to the minus 4.
I get confused by the dashed line being above previous lines you have drawn there.
Mm-hmm.
Can you comment a little bit?
Yeah, because actually this, I will come back to this. This means that even if you don't have a black hole domination, you still have some amount of black holes. They don't dominate the evolution of the universe, but they can produce a lot of LSP. So in principle, this would be excluded if you have an LSP. Lightest superparticle, which constitutes the dark matter. This is the assumption from this.
So I thought this was an exclusion plot, right?
Yeah, but what I'm saying is that if but this is very model dependent, right? It depends on the assumption of your supersymmetric model. So these are, let's say, weaker. That's what I was going to draw.
Does it depend on the remnants existence or not?
No. Well, so this line, it does, but this line, it doesn't.
So then in that segment until 10 to the 5, as Nathan said, you don't trust anything.
Yes, exactly. So it's basically
You are
open.
interested not in that full dashed line, but in the window between 10 to the 5 and 10 to the 10?
No, but the thing is that I'm interested in the whole window, because at the end, we don't know what is the specific setup of the standard model, of the supersymmetric model, right? So in principle, this constraint can be modified easily. So what I mean is that these bounds are very model dependent. So in principle, we are not going to consider them to see what happens, yes. Because in principle, you can have other models that change this.
Assumption they are produced more or less at the same time, so they finish evaporating.
Yeah, that's another important assumption that for one of the initial papers I had is like, so the black holes are assumed to have all, sorry, I forgot to mention that. All black holes have the initial mass, the same mass. So it's a monochromatic spectrum, like all black holes having the same mass. But of course, this is a very strong assumption, and we have worked like what happens if you instead you have extended mass distributions, like all black holes form, but you have heavier or lighter black holes in some specific distribution.
So should I be worried that there is lots of freedom in this black hole games, or should I be happy that what is?
I mean, it depends on your point of view. I am very happy that there is basically these models, these constraints are basically, they are not there. I mean, it depends on the model you assume. So there is a lot of freedom when you consider black holes in this window, for instance, or lighter.
But is it special to black holes, or we just don't know anything about?
Yeah, we just don't know anything about what happens before BBN. And then
So
you can use other tools like gravitational waves to look for black holes that are lighter like this.
But then I could put any type of new physics there, right? It
Yeah.
doesn't need to be black holes.
No, it doesn't need to be black holes.
And since I know absolutely nothing about that region, putting a model with a few black holes or something, or putting something totally.
But I guess you're going to tell us how we can learn today if
Yeah.
there was an early domination of black
Yeah.
holes.
Yeah.
That's the point.
Yeah, I just wanted to say what happens if you have, I don't know, different particle processes here. And then there are tools to look for this, like gravitational waves. I think it would be one of the interesting ones. I'm just going to run a bit, because at the end, at that time, this is the black hole, the initial. So in this case, this will be a line here, and it will disappear when black holes evaporate. And the standard model radiation will basically grow because of the black hole. The particles are coming from evaporation, and then you have a new reheating of the universe. And after that, black holes evolve like this. Right. Sorry, the standard model evolves like this. So interestingly, it will tell us that there are basically different regions. If you look, I don't know, for instance, freeze-in or freeze-out models that happens in different regions here. So if something happens here, what happens if, let's say, freeze-in or freeze-out models happen in this region 1 that I'm calling here, is basically what will happen is that you will have an entropy dilution of the final abundance of dark matter. Because when these black holes evaporate, they're injecting a lot of entropy, and then you will have a dilution, so entropy dilution. If a particle process happens in the region 2, what happens is that you have a matter domination, so you have a non-standard cosmology, and then afterwards you also have entropy dilution, because again, black holes emit a lot of particles at the end. So you have matter domination plus entropy dilution, and so on. So the interesting is, for instance, something happens in the region 4, it's like black holes didn't exist. It doesn't matter, because at the end it's a universe which has reheated to a given temperature. That it's like a new initial condition of new reheat universe. It doesn't matter. Yeah.
But sorry, you drew a constant line that went down.
Yes.
But I guess you could cook up another model where the line would have a totally different
Well,
shape.
no, this is, yeah. It depends on how the black holes evaporate, right? Because this is basically telling you this is the black holes. The evaporation is very slow at the beginning and then becomes very fast. So this line is specific for black holes.
But if they were produced at different times, then some would start evaporating earlier, and the curve could be just totally different.
Yes. So what
Then
happens is
how are
that
you going to
this line can change of let's say, this, the amount of how the universe will reheat changes depending on what are the amount of black holes that if they evaporate first or after. So this is something we have already considered.
Okay. I see.
So we have developed some codes that basically do this. It basically tells you how the universe.
Before adding epicycle, you want to see how the baseline model works, right?
Yeah. This is the simplest. This is the simplest case.
If you let me go, I want to learn how the baseline model works.
Yeah. So if, let's say, you have some particle process like dark matter production, then you will have not only the dark matter that is coming from the thermal bath, for instance, if you assume that it somehow interacts with the standard model bath, but also it will, so let's say just an example, which is dark matter. So in this case, if you assume, for instance, some particle process that produces this dark matter, you will have, let's say, a thermal component plus a black hole component. So the question is, well, in principle, let's assume that your dark matter has some sort of interaction with the standard model, so you have the usual freeze-in and freeze-out processes. But if you add the component from black holes, then you will have another source term for the evolution or equation of this dark matter. And this is an example. So why I think this is very interesting to ask is that when you look at these two sources, they have a completely physical behaviors. For instance, the thermal, if you consider, I don't know, freeze-in or freeze-out, what happens is that you, for instance, if you have the yield of the dark matter as function or something, for instance, scale factor or other quantity, is not relevant, it will follow some, let's say this is the thermal distribution, but from freeze-out, it starts from the thermal distribution and freezes out, right? Or you have some sort of freeze-in which starts from 0 and grows at some point. So this is the usual freeze-in mechanism, and this is the usual freeze-out. But this is for the thermal part. For black hole part, what will matter, actually, is that if this is the black hole temperature as function of time, let's say, over the lifetime of a black hole, so it will start sort of constant, and then it will rise very fast. And let's say when you get to the Planck scale, you don't know what happens. But if this is the initial, sorry. initial. So the initial mass, if the mass of the dark matter is smaller than the initial temperature of the black hole, this, let's say here mx, this particle will produce throughout the evolution of the black hole. But if it's heavier than the black hole, so if its mass is larger than the initial temperature of the black hole, it will be produced only at the end, when the black hole crosses this threshold. So you only have a short period in which the black holes will produce these super heavy particles, which is related to when they start, when the final stages, explosive stages occur. So this is more or less like the general idea of what happens for different cases. As an example of, I took dark matter, but at the end, it will not only depend on the interplay between this and this, but also in the interplay when this particle process occur. Because at the end, as I was mentioning, if these occur when black holes are in the final stages, for instance, you can have a lot of entropy dilution, and you can basically ignore this part, right? Because the entropy dilution is so strong that maybe the only thing that really matters is like the dark matter that is coming from the Hawking evaporation.
So the punchline is that black hole evaporation can be the origin of stable dark matter.
Yes.
Okay.
Yeah. Yeah, but at the end, if you want to compute correctly, you need to take into account all these different ingredients. Mm-hmm. Because it's not simply saying, oh, I forget about this and only include this. You also need to include how the background is changing, because the entropy dilution can be very strong.
So there will be a range of dark matter mass that you are going to tell us.
Yeah. So yeah, I have some sort of problem. Probably I can end this with this. So when we computed what is the different range, so let me just do, I'm going to zoom in this region of my parameter space, and I will vary what is the dark matter mass. So I will stop at 10 to the 9. 10 to the minus 1. 10 to the minus 95. 1. At some point here is BBN. So the first thing that we realized is that it actually, if you want to have basically the whole dark matter coming from the Hawking evaporation, it will depend on the particle, what is the type of particle, if these particles are fermion scalars or vectors. Because I was talking before, and now the plot that I just erased, the amount of particles that are produced, it depends on the spin of this particle, because the production of a scalar particle is much easier than the production of vector for a Schwarzschild black hole. Right? So in principle, if you want to draw, for instance, lines for a given mass of the dark matter, let me just do this. Sorry, this is not to scale. If you have, for instance, a dark matter with the mass of 10 MeV, and I will come back to this mass, it means that, for instance, you don't need a large amount of black holes. So let me just put the numbers here. It's like 10 to the minus. And then this is the region of PBH domination. So this is telling you basically that the amount of black holes that you require for a given mass of the dark matter, it really depends on the particle spin, if it's a scalar fermion or a vector. And also, you see that here it becomes constant. The reason it becomes constant is that if you had this domination of black holes in the early universe, it's like it doesn't matter what is the amount of radiation you had before. As I was talking, this process becomes bleeding, not only because of entropy dilution, but also because what it will dominate the production of dark matter is the Hawking evaporation. So this is why these lines become constant. But if, for instance, these black holes didn't dominate, but I don't know, they have a smaller amount, but a significant amount, they can still have this production of dark matter. But of course, this is very light, right? This is 10 MeV. So there is a big constraint here, which is since basically the energy of these particles that are produced from the black hole would be related to the black hole temperature, this dark matter can be very boosted. So actually, for instance, I know that I chose this value, but this value is excluded because it's a very warm dark matter. So in principle, you have that, you can produce this, and you see that you can have some parameters to produce this dark matter, but in principle, you encounter this type of constraints like warm dark matter. But for instance, if you want a heavier dark matter, let's say 10 to the 7. Let me just first draw this. So this is for a scalar, scalar 10 to the 7 GeV. You see that the amount of black holes you require is much less. Of course, it's because since basically you have that this is a larger mass, in order to give the correct observed relic abundance, you need less amount of dark matter at the end. So as you can see, there are also two different behaviors here. And this mass here, so let me just, when there is this change of behavior is when the initial black hole is equal to the mass of the dark matter. So, sorry, I was calling it X. So basically here, this behavior happens when you are in this situation, when the black hole is emitting during its whole lifetime, this particle X, and you have a different behavior. I have the analytic formula, but I think it's important. When the amount of black hole, the dark matter, is only produced in the final stages.
Is 10 to the 5 gram light enough to give a high enough temperature to produce
yes.
that?
Yes. Yeah, you're right. The temperature of a black hole is 1 GeV for a black hole of 10 to 13 grams.
So, okay, that's the kind of a limit, no?
Yes.
Because if you go to 10 to the 5 gram, you get a 10 to the 8, so 10 to the 8 GeV is kind of limit.
Yeah, exactly. But again, you can have super heavier dark matter, and then it's only produced in the final stages. So you need more, the larger amount of black holes, yes. Okay, so just to quickly end. So how can we test all this, right? So interestingly, these black holes would also source gravitational waves. One way to source gravitational waves is that if you assume that, of course, black holes also emit gravitons, this will be part of this, the Hawking radiation. So black holes will emit also gravitons, and these gravitons, let's say, theoretically, could be also detected. So the thing is that when you compute what it would be the spectrum of gravitons, you find that there are values that are huge frequencies. So, yeah, it's like, yeah, the omega, it's 10 to the 14 hertz.
No, the slope. Omega I guess the spectrum is blue, no? Because you have much phase space, no?
Yeah.
And it's omega to the cube, omega to the fourth, you know?
I don't actually know the actual value. Maybe, yeah, I can just draw quickly. Yeah, so for instance, you can have gravitational waves from Hawking radiation, and the spectrum you find is like 10 to minus 8. It's 10 to the 11. 10 to the 17 of frequency in hertz. So this is very, very high frequency gravitational waves. And for a black hole that had an initial mass of 1 gram, 10 to the 14, here, we have like this shape. And for a heavier black hole, so this would be, in principle, a way to try to see if you are able to detect these very high frequency gravitational waves. Would be a way to test. But it's very complicated, I guess.
Sorry, a very naive question. I always thought Hawking radiation was just purely theoretical, that it was, in practice, not realistic to expect to measure.
Well,
am I wrong? That,
well, this is a possibility to detect. I mean, you need experiments looking for this high frequency. But in principle, there would be, of course, it depends in assuming that there were a population of black holes in the early universe.
so it's not polluted by astrophysics around these black holes and stuff. It's very, I see.
Yes.
Yeah, but there's no device that is sensitive.
Yeah, this is huge. But there is another type of gravitational waves that come from the so-called poltergeist mechanism, which I'm not very familiar with, but this is something we have been working on. I just want to show you this end. So this mechanism basically comes from the fact that if you had the evaporation, here you have a sudden transition between a matter-dominated universe to a radiation-dominated universe. So your gravitational potential can be resonantly enhanced, produce a resonance of gravitational waves. It's a bit tricky, to be honest. It's a bit complicated. I haven't fully understood it. But what these people have demonstrated, so what we have done is basically propose this, the production of dark matter. But they have shown that if these black holes really dominated and you had this transition, you can produce gravitational waves that would be in a region that could be detectable in the, let's say, near future. So let me just also gravitational. So basically, let me just draw one example. So in principle, from this paper, actually, let me just quote. So quite recent, they have shown that if you, because of the sudden transition between a matter and a radiation-dominated universe, you have the enhanced production of these gravitational waves. And the interesting thing is that they show that they could be, for instance, for a black hole of a mass of 10 to the 4 gram, they would produce some spectrum that could be seen in future experiments like BBO, but not least, but BBO and other future gravitational wave detectors. So in principle, it's interesting because at the end, it would be a way to test if you had this population of black holes, it would be a way to test, for instance, particle process like dark matter, right? Because if you find, let's say, this gravitational wave with some specific shape, you know that this particle, the black holes existed, and if you assume, of course, Hawking radiation, you need to include it in your particle process, as I was saying, like production of dark matter or even, I don't know, production of baryon asymmetry via, let's say, leptogenesis scenarios. So yeah, so this is a way to do that. And also there are handles, but I don't have much time. They're saying that if you have, for instance, these gravitons are very high in frequency, so they also would modify delta N effective in the early universe, right? So in principle, you can also have constraints from delta N effective in the future because of this production of these very hot gravitons in the early universe. So yeah, so that was it.
the very beginning, no, you need some large fluctuation in the density at a very, very tiny scale, order of the meter, probably, something like that.
Yeah.
So what would give you that large fluctuation in the primordial density spectrum?
Yeah, I don't think it's still very clear. It's more, well, people have like cooking models like with inflation that can do that without spoiling the effect on CMB. So such a way that you have these high perturbations, and then
qualitatively, what is the physical effect that could give you a spike in the density?
Yeah, so if you're, as I was saying, if you're, the shape of the potential, of the inflaton potential has some specific feature, like it becomes sort of constant, but not exactly constant, so there is an ultra slow roll, then at that point you can have the production of very high perturbations.
On very small scales.
Yes. Yeah, of course, you need to fine-tune it in such a way that this ultra slow roll happens for some specific scales. Yeah, which one you're interested in. Yeah, but as I was saying, it's just one candidate for this.
Okay.
For me, it was really interesting to know that Hawking radiation could be observed. I had no idea, but so that's fascinating to know that if the black hole is light enough, but not too light, there is a window where we could, in principle, observe it. But I'm confused from there to a curve like that, where you assume really a precise profile, like all black holes disappear at the same time, etc., versus, for example, a triangle or a totally different shape. It looks so arbitrary that it looks strange that you are trying to describe it quantitatively with a model and not just as a mechanism where you just say, if I have something going down. I'm a bit puzzled by what's the advantage of having a model if there is so much uncertainty about when the black holes are produced, what type of black holes, what's their properties, etc. What are the rules of the game?
I mean, so the shape of this curve, as I was saying, is only derived because of this dependence, right? The fact that this line starts first as a constant and then rapidly decreases comes from the fact that the Hawking evaporation, the dependence on the mass, is 1 over m squared, right? This is only telling you that at the beginning, Hawking evaporation is not very efficient, but at the end, it becomes efficient.
That's assuming all black holes are produced at the same time with the same mass.
Yes, yes. Yeah, of course.
Isn't that super?
Yeah, I completely agree, and we have a work that we have relaxed this assumption in which you have different, mass spectrum. Because at the end, this mass spectrum is assumed to have a monochromatic, so a Dirac delta, but you can have some, inflation models predict a log normal distribution, like for instance. So yeah, in that case, this feature will change, because at the end you will have some sort of not as fast as this, right? Or if you have other types of mass distribution, how this shape changes will depend on that. And this is something we have already worked on. Like showing what happens first here in this, the evaporation of black holes if you have extended distributions, and what happens if, for instance, you have the production of dark matter or, leptogenesis or dark radiation. So this is, I completely agree that this is very arbitrary to say that all black holes have the same mass, and this, we already have worked on that and relaxed that assumption.
So just to get some numbers out, you said that it's much more efficient when it's small, right? The black hole, right?
You mean this here?
Yep.
Yes.
Yeah. So can you integrate it and tell me what % of the radiation comes before it comes, the Planck scale, and what after?
Yeah, but let me just, because there is a cubic dependence. Let me just, I had written how is the dependence on the mass.
No, but here the Planck regime doesn't contribute to
No, it's very, yeah.
So what is it, 99%, or is it?
Probably more than that, yeah.
Okay,
I can give you the number, but I will need to compute it. Where is that?
Okay. No, if you can estimate, if you tell me 99%.
Yeah, because it's. When you solve this equation of the thing, let's assume that this is a constant, so the solution of this equation is analytic. Right? The time t, so this would be like this cube. So in principle, you can compute if this is, let's say we want this to be en Planck, right? So I think it's
T over tau?
tau is the lifetime of the black hole. Sorry, forgot to write. Which is a huge number. Well, it's proportional. I'll put numbers. I think how to compute.
Okay.
Yeah, I guess. So yeah, that's the lifetime of the black hole.
No, Pedro answered the question. So the energy of radiation is just
But the energy radiation of a black hole, you can
it's
take
the
a
rate
bit.
that changes,
Yeah.
but not the, you know.
Yeah, I can estimate it, but I can give you. It's probably 99% because at the end, even
No, I
though
think
that.
Pedro answered the question. It's
yeah.
just the ratio of the M.
Yeah. Yeah. Because at the end, I would need to compute that.
So what experiment are trying to measure Hawking radiation? Is just a CBO? What is the